let's see if we can use everything we know about differentiation and concativity and maximum and minimum points and inflection points to actually graph a function without using a graphing calculator. So let's say our function, let's say that f of x is equal to 3x to the fourth minus 4x to the third plus 2. And of course, you could always graph a function just by trying out a bunch of points. But we want to really focus on the points that are interesting to us. And then just to get the general shape of the function, especially we want to focus on the things that we can take out from this function using our calculus toolkit or our derivative toolkit. So the first thing we probably want to do is figure out the critical points. We want to figure out, I'll write it here, critical points. And just as a refresher of what critical points means, it's the points where the derivative of f of x is 0. So critical points are f prime of x is either equal to 0 or it's undefined. Or if it's undefined. This function looks differentiable everywhere. So the critical points that we worried about are probably, well, I can tell you, they're definitely just the points where f prime of x are going to be equal to 0. This derivative, f prime of x, is going to actually be defined over the entire domain. So let's actually write down the derivative right now. So the derivative of this, f prime of x, this is pretty straightforward. The derivative of 3x to the fourth, 4 times 3 is 12. 12x to the, we'll just decrement the 4 by 1, 3. Right? You just multiply times the exponent and then decrease the new exponent by 1, minus 3 times 4 is 12, times x to the 1 less than 3 is 2. And then the derivative of a constant, the slope of a constant, you can almost imagine, is 0. It's not changing. A constant, by definition, isn't changing. So that's f prime of x. So let's figure out the critical points. The critical points are where this thing is either going to be equal to 0 or it's undefined. Now, I could look over the entire domain of real numbers, and this thing is defined pretty much anywhere. I could put any number here, and it's not going to blow up. It's going to give me an answer to what the function is. So it's defined everywhere. So let's just figure out where it's equal to 0. So f prime of x is equal to 0. So let's solve which x is. So let's solve, well, I don't have to rewrite that. I just wrote that. Let's solve for when this is equal to 0. And I'll do it in the same color. So 12 x to the third minus 12 x squared is equal to 0. And so let's see what can we do to solve this. Well, we could factor out a 12x. So if we factor out a 12x, then this term becomes just x. And then actually, let's factor out a 12x squared. If we factor out a 12x squared, if we divide both of these by 12x squared, this term just becomes an x. And then minus 12x squared divided by 12x squared is just 1, is equal to 0. I just rewrote this top thing like this. You could go the other way. If I distributed this 12x squared times this entire quantity, you would get my derivative right there. So the reason why I did that is because to solve for 0, or if I want all of the x's that make this equation equal to 0, I now have written it in a form where I'm multiplying one thing by another thing. And in order for this to be 0, one or both of these things must be equal to 0. So 12x squared are equal to 0, which means that x is equal to 0 will make this quantity equal 0. And then the other thing that would make this quantity 0 is if x minus 1 is equal to 0. So x minus 1 is equal to 0 when x is equal to 1. So these are our two critical points. Our two critical points are x is equal to 0 and x is equal to 1. And remember, those are just the points where our first derivative is equal to 0, where the slope is 0. They might be maximum points, they might be minimum points, they might be inflection points. We don't know. They might be, if this was a constant function, they could just be anything. So we really can't say a lot about them just yet. But they are points of interest. I guess that's all we can say, that they are definitely points of interest. But let's keep going and let's try to understand the concativity, and maybe we can get a better sense of this graph. So let's figure out the second derivative. So the second, I'll do that in, let me do it in this orange color. So the second derivative of my function f let's see, 3 times 12 is 36x squared minus 24x. So let's see, well, there's a couple of things we can do. Now that we know the second derivative, we can answer the question, is my graph concave upwards or downwards at either of these points? So let's figure out what at either of these critical points. And it'll all fit together. Remember, if it's concave upwards, then we're kind of in a U shape. If it's concave downwards, then we're in a kind of upside down U shape. So f prime prime, our second derivative at x is equal to 0 is equal to what? It's equal to 36 0 squared minus 24 times 0. So that's just 0. So f prime prime, so it's just equal to 0. So we are neither concave upwards nor concave downwards here. It might be a transition point, it may not. If it is a transition point, then we're dealing with an inflection point. We're not sure yet. Now let's see what f prime prime, or our second derivative evaluated at 1 is. So that's 36 times 1. Let me write it down. That's equal to 36 times 1 squared, which is just 36, minus 24 times 1. So it's 36 minus 24. So it's equal to 12. So this is positive. Our second derivative is positive here. It's equal to 12, which means our first derivative, our slope, is increasing. The rate of change of our slope is positive here. So this, at this point, right here, we are concave upwards. Upwards. Which tells me that this is probably a minimum point, right? The slope is 0 here, but we are concave upwards at that point. So that's interesting. So let's see if there are any other potential inflection points here. We already know that this is this is a potential inflection point. Let me circle it in red. It's a potential inflection point. We don't know whether our function actually transitions at that point. We'll have to experiment a little bit to see if that's really the case. But let's see if there are any other inflection points. So to figure that, or potential inflection points. So let's see if this equals 0 anywhere else. So 36x squared minus 24x is equal to 0. Let's solve for x. Let us factor out we can factor out 12x. 12x times 3x, right? 3x times 12x is 36x squared minus 2 is equal to 0. So these two are equivalent expressions. If you multiply this out, you'll get this thing up here. So this thing is going to be equal to 0 either if 12x is equal to 0. So 12x is equal to 0. That gives us x is equal to 0. So at x equals 0, this thing equals 0. So the second derivative is 0 there. And we already knew that because we tested that number out. Or this thing. If this expression was 0, then the entire second derivative would also be 0. So let's write that. So 3x minus 2 is equal to 0. 3x is equal to 2. Just adding 2 to both sides. 3x is equal to 2/3. So this is another interesting point that we haven't really hit upon before. That might be an inflection point. And the reason why I say it might be is because the second derivative is definitely 0 here. You put 2/3 here, you're going to get 0. And what we have to do is see whether the second derivative is positive or negative on either sides of 2/3. And we already have a sense of that. I mean, we could try out a couple of numbers. We know that, if we say that x is greater than 2/3, let me scroll down a little bit just so we have some space. So let's see what happens. When x is greater than 2/3, x is greater than 2/3, what is f prime of x? So let's see. Or, sorry, what is f prime prime? What is the second derivative? So let's try out a value that's pretty close, just to get a sense of things. So let me rewrite it. F prime prime of x is equal to, let me write it like this. I mean, I could write it like this, but this might be easier to deal with. It's equal to 12x times 3x minus 2. So if x is greater than 2/3, this term right here is going to be positive. That's definitely, any positive number times 12 is going to be positive. But what about this term right here? 3 times 2/3 minus 2 is exactly 0, right? That's 2 minus 2. But anything larger than that, 3 times, if I had 2.1/3, right? So if here, this is going to be a positive quantity. Any value of x greater than 2/3 will make this thing right here positive, right? This thing is also going to be positive. So that means that when x is greater than 2/3, that tells us that the second derivative is positive. It is greater than 0. So in our domain, as long as x is larger than 2/3, we are concave upwards. And we saw that here. At x is equal to 1, we were concave upwards. But what about x being less than 2/3? So when x is less than 2/3, let me write it. Let me scroll down a little bit. When x is less than 2/3, what's going on? I'll rewrite it. F prime prime of x, second derivative, 12x times 3x minus 2. Well, if we go really far less, we're going to get a negative number here, and this might be negative. But let's see if we just go really right below 2/3, when we're still in the positive domain. So if this was like 1.9 thirds, which is a mixture of a decimal and a fraction, or even 1/3, this thing is still going to be positive. Right below 2/3, this thing is still going to be positive. We're going to be multiplying 12 by a positive number. But what's going to be going on? What's going on right here? What's going on right here? At 2/3, we're exactly 0. But as you go anything less than 2/3, 3 times 1/3 is only 1. 1 minus 2, you're going to get negative numbers. So when x is less than 2/3, this thing right here is going to be negative. So the second derivative, if x is less than 2/3, the second derivative, right to the left, or right when you go less than 2/3, the second derivative of x is less than 0. Now the fact that we have this transition from when we're less than 2/3, we have a negative second derivative, and when we're greater than 2/3, we have a positive second derivative. That tells us that this indeed is an inflection point. That x is equal to 2/3 is definitely an inflection point for our original function up here. Now, we have one more candidate inflection point, and then we're ready to graph. Then, once you know all the inflection points and the maximum minimum, you are ready to graph the function. So let's see if x is equal to 0 as an inflection point. We know that the second derivative is 0 at 0. But what happens above and below the second derivative? So let me do our little test here. So when x is, let me draw a line so we don't get confused with all of this stuff that I wrote here. So when x is greater than 0, what's happening to the second derivative? Remember, the second derivative was equal to 12x times 3x minus 2. I like writing it this way because you've kind of decomposed it into two linear expressions, and you can see whether each of them are positive or negative. So if x is greater than 0, this thing right here is definitely going to be positive. And then this thing right here, right when you go right above x is greater than 0. So we have to make sure to be very close to this number, right? So if this number is like let's say it's 0.1. Right? So you're right above 0. So this isn't going to be true for all of x greater than 0. We just want to test exactly what happens right when we go right above 0. So if this was 0.1, you would have 0.3. 0.3 minus 2, that would be a negative number. Right? So right as x goes right above 0, this thing right here is negative. So as x is greater than 0, you will have your second derivative is going to be less than 0. You're concave downwards, which makes sense because at some point we're going to be hitting a transition. Remember, we were concave downwards before we got to 2/3, right? So this is consistent. From 0 to 2/3, we are concave downwards, and then at 2/3, we become concave upwards. Now let's see what happens when x is when x is just barely less than 0. So once again, f prime, the second derivative of x is equal to 12x times 3x minus 2. Well, right, if x was minus 0.1 or minus 0.001, no matter what, this thing is going to be negative. This expression right here is going to be negative. The 12x, right? You have some negative value here times 12. It's going to be negative. And then what's this going to be? Well, 3 times minus 0.1 is going to be minus 0.3. Minus 2 is minus 2.3. You're definitely going to have a negative. This value right here is going to be negative. And then when you subtract from a negative, it's definitely going to be negative. So that is also going to be negative. But then if you multiply a negative times a negative, you're going to get a positive. So actually, right below x is less than 0, the second derivative is positive. The second derivative is positive. Now, this all might have been a little bit confusing, but we should now have the payoff. We now have the payoff. We have all of the interesting things going on. We know that at x is equal to 1, we know that at x is equal to 1, let me write it over here. We figured out at x is equal to 1, the slope is 0. So f prime prime is, sorry, let me write it this way. I should have said, we know that the slope is 0. Slope is equal to 0, and we figured that out because the first derivative was 0. This was a critical point. And we know that we're dealing with the function is concave upwards at this point. And that tells us that this is going to be a minimum point. So what is f of, and we should actually get the coordinates so we can actually graph it. That was the whole point of this video. So, and f of 1 is equal to what? F of 1, let's go back to our original function, is 3 times 1, right? 1 to the 4th is just 1. 3 times 1 minus 4 plus 2, right? So 4 times. So it's well, 3 times 1 minus 4 times 1, which is minus 1, plus 2. Well, that's just a positive 1. So f of 1 is 1. And then we know at x is equal to 0, we also figured out that the slope is equal to 0. But we figured out that this was an inflection point, right? The concativity switches before and after. So this is an inflection point. Inflection point. And we are concave below 0. Below 0. So when x is less than 0, we are upwards. We are upwards. Our second derivative is positive. And when x is greater than 0, we are downwards. We are concave downwards, right above. Not for all of the domain x and 0, just right above 0, downwards. And then what is f of 0? Just so we know, because we want to graph that point. F of 0. Let's see, f of 0, this is easy. 3 times 0 minus 4 times 0 plus 2. Well, that's just 2. F of 0 is 2. And then finally, we got the point x is equal to 2/3. X is equal to, let me do that in another color. We had the point x is equal to 2/3. We figured out that this was a inflection point. The slope isn't necessarily, or the slope definitely isn't 0 there because it wasn't one of the critical points. And we know that we are downwards. We know that when x is less than 2/3, or right less than 2/3, we are concave downwards. And when x is greater than 2/3, we saw it up here. When x was greater than 2/3, right up here, we were concave upwards. The second derivative was positive. We were upwards. And we could actually figure out what's f of 2/3. That's actually a little bit complicated. We don't even have to figure that out, I don't think, to graph. I think we could do a pretty good job of graphing it just with what we know right now. So that's our takeaways. Let me do a rough graph. Let's see. So let me do my axes, just like that. So let's see, we're going to want to graph the point 0, 2. So let's say that the point 0, 2, so this is x is equal to 0, and we go up 1, 2. So this is the point 0, 2. Maybe I'll do it in that color, the color I was using. So that's this color. So that's that point right there. Then we have the point x. We have f of 1, which is the point 1, 1. Right? So this point right here is, we'll go up 1. So that's the point 1, 1. This was the point 0, 2. And then we have the x is equal to 2/3, which is our inflection point. So when x is 2/3, we don't know exactly what number f of 2/3 is. Might be here someplace. Let's say f of 2/3 is right there. So that's the point 2/3. And then whatever f of 2/3 is, it looks like it's going to be 1 point something. F of 2/3. You could calculate it if you like. You just have to substitute back in the function. But we're ready to graph this. We're ready to graph this thing. So we know that at x is equal to 1, the slope is 0. We know that the slope is 0. It's flat here. And we know it's concave upwards. So we're dealing, it looks like this. It looks like that over that interval. We're concave upwards. And we know we're concave upwards from x is equal to 2/3 and on. Right? Let me do it in that color. We knew x equal to 2/3 and on, we're concave upwards. And so that's why I was able to draw this U shape. Now we know that when x is less than 2/3 and greater than 0, we're concave downwards. So the graph will look something like this. Over this interval will be concave downwards. Let me draw it nicely. over this interval, the slope is decreasing. And you can see it if you keep drawing tangent lines. It's flattish there. It gets negative, more negative, more negative, more negative, until the inflection point, and then it starts increasing again because we go back to concave upwards. And then finally, the last interval is below 0. And we know below 0, when x is less than 0, we're concave upwards. So the graph looks like this. The graph looks like that. And we also know that x is equal to 0 was a critical point. The slope was 0. So this graph is actually flat right there, too. So this is an inflection point where the slope was also 0. So this is our final graph. We're done. After all that work, we were able to use our calculus skills and our knowledge of inflection points and concativity and transitions in concativity to actually graph this fairly hairy-looking graph. But this should be kind of what it looks like if you graph it on your calculator.
So I've got a 10-foot ladder that's leaning against a wall, but it's on very slick ground, and it starts to slide outward. And right at the moment that we're looking at this ladder, the base of the ladder is 8 feet away from the base of the wall, and it's sliding outward at 4 feet per second. And we'll assume that the top of the ladder kind of glides along the side of the wall. It stays kind of in contact with the wall and moves straight down. And we see right over here the arrow is moving straight down. And our question is, how fast is it moving straight down at that moment? So let's think about this a little bit. What do we know and what do we not know? So if we call the distance between, let's call the distance between the base of the wall and the base of the ladder, let's call that x. We know right now x is equal to 8 feet. We also know the rate at which x is changing with respect to time. The rate at which x is changing with respect to time is 4 feet per second. So we could call this dx dt. Now let's call the distance between the top of the ladder and the base of the ladder h. Let's call that h. So what we're really trying to figure out is what dh dt is, given that we know all of this other information. So let's see if we can come up with a relationship between x and h, and then take the derivative with respect to time, maybe using the chain rule, and see if we can solve for dh dt knowing all of this information. Well, we know the relationship between x and h at any time because of the Pythagorean theorem. We can assume this is a right angle, so we know that x squared plus h squared, x squared plus h squared is going to be equal to the length of the ladder squared, is going to be equal to 100. And what we care about is the rate at which these things change with respect to time. So let's take the derivative with respect to time of both sides of this. So we're doing a little bit of implicit differentiation. So what's the derivative with respect to time of x squared? Well, the derivative of x squared with respect to x is 2x, and we're going to have to multiply that times the derivative of x with respect to t, dx dt. Just to be clear, this is a chain rule. This is the derivative of x squared with respect to x, which is 2x, times dx dt to get the derivative of x squared with respect to time, just the chain rule. Now similarly, what's the derivative of h squared with respect to time? Well, that's just going to be 2h. The derivative of h squared with respect to h is 2h times the derivative of h with respect to time. Once again, this right over here is the derivative of h squared with respect to h times the derivative of h with respect to time, which gives us the derivative of h squared with respect to time. And what do we get on the right-hand side of our equation? Well, the length of our ladder isn't changing. This 100 isn't going to change with respect to time. The derivative of a constant is just equal 0. So now we have it, a relationship between the rate of change of h with respect to time, the rate of change of x with respect to time, and then at a given point in time when the length of x is x and h is h. But do we know what h is when x is equal to 8 feet? Well, we can figure it out. When x is equal to 8 feet, we can use the Pythagorean theorem again. We get 8 feet squared plus h squared is going to be equal to 100. So 8 squared is 64. Subtract it from both sides. You get 8 squared is equal to 36. Take the positive square root. A negative square root doesn't make sense because then the ladder would be below the ground. It would be somehow underground. So we get h is equal to 6. So this is something that was essentially given by the problem. So now we know. We can look at this original thing right over here. We know what x is. That was given. Right now, x is 8 feet. We know the rate of change of x with respect to time. It's 4 feet per second. We know what h is right now. It is 6. So then we can solve for the rate of h with respect to time. So let's do that. So we get 2 times 8 feet times 4 feet per second. 4 feet per second. So times 4 feet per second. 4 feet per second. So times 4 plus 2h. So plus 2h is going to be plus 2 times our height right now is 6 times the rate at which our height is changing with respect to t is equal to 0. And so we get 2 times 8 times 4 is 64 plus 12 dh dt is equal to 0. We can subtract 64 from both sides. We get 12. 12 times the derivative of h with respect to time is equal to negative 64. Negative 64. And then we just have to divide both sides by 12. And so now we get a little bit of a drum roll. The derivative, the rate of change of h with respect to time is equal to negative 64 divided by 12. Is equal to negative 64 over 12, which is the same thing as negative 16 over 3. Yep, that's right. Which is equal to, let me scroll over to the right a little bit, negative 5 1/3 feet per second. Feet per second. So we're done. But let's just do a reality check. Does that make sense that we got a negative value right over here? Well, our height is decreasing. Our height is decreasing, so it completely makes sense that its rate of change is indeed negative. And we're done.